Hey guys, Mr. Davis here again. So this is going to be part two of our discussion on the oceans and ocean water. In the last series, we talked about the circulation of ocean water around the planet, how that helps regulate global temperatures. I'm going to go ahead and review a little bit about ocean water, and then we're also going to talk about fresh water, where the fresh water is found, and then conservation of mass and energy in the biosphere. All right, so first up, the difference between ocean water and fresh water is that ocean water contains more salt. All right, if you've ever been to the beach, you've ever been to the ocean, you know that the ocean water is, well, salty. It tastes like it has more salt in it. Salinity then is the term that we're going to use to measure that. So salinity is the measure of the amount of dissolved salts in a given amount of liquid, and this is measured in parts per thousand. Salinity is lower in places that get a lot of rain, where fresh water flows into the sea. Salinity is higher where water evaporates rapidly and leaves the salts behind. Okay, this should be a little bit of review for you. This should be pretty straightforward, but I wanted to make sure I touched on it again. So, most of the salt in the ocean is going to be sodium chloride, which makes up um, which is made up of the elements sodium and chlorine. There may be other elements found in there as well. You might also have potassium, and there's dissolved iron, and there's dissolved calcium as well. There's a number of different things that are found in the ocean, but the majority of those dissolved minerals are going to be chlorine and sodium. All right, they are ionic compounds. If you dry the salt water out, if you dry the ocean water out, you get left behind crystals of salt, and that's where that natural sea salt for tables and for cooking and stuff like that comes from. All right. All right. So then the ocean is going to be divided up based off of temperature zones. Okay. So let's go ahead and talk about how we divide the ocean up. The surface of the ocean is going to be warmed by the sun. While the deeper you go, the colder it gets. When you get down to the very bottom of the ocean where sunlight never reaches, all right, it is generally just above freezing. It is extremely cold down there. All right. You're not going to have any inputs really of heat from the surface descending down that far. But at the same time, due to the level of salinity, due to the pressure, due to other factors, it's never going to freeze. And because it's never going to freeze, it's kind of a weird thing where it's going to just stay at that temperature. All right. It is going to be just a degree or two above freezing. And yeah, surface waters are stirred up by waves and currents. So the surface zone may be as much as 350 meters deep. It really depends on where you are and the nature of that water. Level of salinity, level of particulates dissolved in there, a couple other factors. Below the surface zone, though, there's a region called the thermocline. And this is a little confusing also because we refer to any time you have a dramatic shift in temperature in a water column as being a thermocline, but the thermocline is a layer from about 300 to 700 meters deep where the temperature just descends rapidly. All right. It goes from being near the surface temperature to just plummeting down to near freezing temperatures. So to see what this looks like, we can look at how the temperature zones divide any body of the ocean up based on that. You have the surface zone up at the top where the temperature is relatively constant. Then you've got this thermocline region where you have a rapid drop in temperature. And then you have the deep zone where it usually averages just about 2 degrees above freezing. Sometimes it extends almost all the way to freezing temperatures. But again, salinity and pressure can keep that liquid. All right. It's kind of the opposite of the core of the Earth. It's a little weird, I know. It gets colder the deeper it goes. At that bottom layer, it goes all the way down to the bottom, deepest part of the ocean's almost 7 miles deep or so. And yeah, it averages around just 2 degrees Celsius, just above freezing. All right, so that's going to wrap up our information on the ocean. Now let's talk about river and freshwater systems. So freshwater is water that contains an insignificant amount of salt. Like there's just not much salt in it. Most of the freshwater is locked up in ice caps and glaciers, while the rest is found in lakes, rivers, wetlands, the soil, and the atmosphere. 97% of the water on Earth is salt water. Of that remaining 2 to 3% of water on Earth that is freshwater, 90% of that is bound up in frozen glaciers, and then the majority of it is also underground in what are called aquifers. When we refer to a river system, what we're talking about is a network of streams that drain an area of land, and they all drain to a main river, and then all the smaller ones drain into larger ones. They're called tributaries. In the United States, we've got a couple of them. The biggest river system, though, is the Mississippi River system. It's got literally hundreds of tributaries that all flow into it. We've got tons and tons and tons of rivers that flow all the way to the Mississippi. Um, and they actually start basically on the eastern slope of the Rockies all the way over to the Appalachian Mountains, basically North Carolina, and that all flows into the Mississippi River Basin. And so that creates a huge outflow in the Mississippi River that flows right through most of America's farmland. So that water is used for farming. It's pulled out of the rivers and it flows back into the rivers when water runs off those fields. And we can find the traces of this, and I've talked about this before. Then you have groundwater. Groundwater is water that's found, well, underground. I know, that's such a complicated thing, right? Groundwater is water found underground. All right. Rain and melting snow run off the ground, off the land, but a lot of this water will trickle down through the rocks and collecting groundwater. Areas where you've got a lot of trees, like forests and things like that, you're going to get more water percolating down into the ground because they'll actually follow the channels from those roots. You've got the loose soil there that gets tilled easily from the action of those roots and things burrowing through there. So you're going to get that water dripping down through. Although groundwater makes up about 1% of the total water on Earth, yeah, so about 1% of the water on Earth is actually groundwater, it does fulfill a huge need for human fresh drinking water, and it supplies the majority of agricultural needs. And in fact, this is really important for us here in Arizona because the majority of our local communities, including Chandler, get a huge portion of their water from groundwater. We pump this water out constantly. Maybe you've driven around town and you've seen those weird things where you have that pipe that just sticks out of the ground and then arcs over, and sometimes you see water flowing out of there into like some sort of catch basin that then goes off to a canal or something. Yeah, that's groundwater. That's a well that's being pumped up. And so all of this is trapped in something called an aquifer, and that's a layer of rock that stores water and allows the flow of groundwater. And here's a map of the major aquifers on Earth. Now, this is a two-dimensional map, and this is a problem because we're talking about going down into the Earth. So this does not talk about how deep those aquifers go. So some of these aquifers are very far underground and they're very narrow. Other aquifers here are very close to the surface and they extend like way, way, way down. So I want to draw your attention really quickly using my little laser pointer here. So you see this band of an aquifer that runs all the way down through here, okay? That blue there, that is part of an aquifer system called the Ogallala Aquifer. And I love that name because it's just fun to say. The Ogallala Aquifer is one of the largest aquifers on the planet. It extends deep underground, but it starts in most places relatively shallow. There are a number of places in the aquifer where it is less than 10 feet underground. So if you dug 5-6 feet down, you're going to hit groundwater, and that water is just going to pour into that hole that you dug into the ground. Here in Arizona, our water table is sometimes 300 meters underground. All right, so that's like 900 feet. We got to drill way, way, way down to get to that water table. All right, and the water table is the level at which the rocks become saturated. All right, and we will talk about this when we talk more about hydrology. All right, so that's going to bring us to the biosphere. Now, most of the biosphere can't access that, but it does rely heavily on fresh water. It does rely on rivers, lakes, streams, and precipitation. So the biosphere is the part of the Earth where life exists and extends about 12 kilometers into the ocean, about 9 kilometers up into the atmosphere, so basically 7 miles down underwater, and it extends all the way up to about 3 miles or so above, and it's just this band, and that's where all life on Earth exists. The materials that organisms require must be continuously recycled. So our gravity on our planet, as well as our electromagnetic field, allows us to maintain all the matter on Earth. It doesn't just go floating off into space. But at the same time, what we have on Earth is what we have. And if we overuse a resource, we can run out. We can run out of fresh available water. We can run out of usable, healthy air. We can run out of healthy soil in which plants can grow. If those things are overused, they are affected by other things that we do. Like if we were to cut down too many forests, trees, or grasslands, that could impact the soil, and that soil could literally blow away, wash into the ocean, those kind of things, and it's not there, and can't plant plants on bare rock. So suitable combinations that organisms need to survive are found only in this thin, small biosphere. And guys, at this point, this is the only place we've discovered life in the universe. So this biosphere is this narrow band that goes all the way around the Earth. It is this thin film, this just small veneer of living organisms clinging to a giant rock with a burning hot center, hurtling through space at millions of miles an hour, and that's it. So if we don't protect it, we don't take steps to ensure its viability, then we have a very real risk of not having a biosphere that can support, most importantly, us. It's not that our planet will cease to exist. It's not that life on Earth will necessarily cease to exist, because life has been found clinging to our planet in all kinds of crazy places. The thing is, the more we change our planet, the more we trash our biosphere, harder it's going to be for us to survive. So the biosphere is located close to Earth's surface because that's where the sunlight is. Plants need sunlight to produce food, and every other organism gets its food from plants. Yeah, so even when you eat meat, you're technically eating plants, because that meat, that animal that you're eating, it had to eat a plant first. So most of the algae that float on the surface of the ocean is known as phytoplankton, and that is the basis of the food chain for most of the Earth. The energy used by these organisms must be obtained in the biosphere, and it must be continuously supplied for life to continue. We get a constant input of energy from the sun, but when an organism dies, the nutrients, the minerals that are in its body, have to be broken down and recycled in order to be used by other organisms. And in order to break down those minerals and recycle them and use them again, energy has to be supplied. And the energy flow in Earth is basically what's turning this engine that's running this biomechanical, organic recycling plant that we live on. So that's the last thing we're going to talk about here, is the energy flow in the ecosystem. Remember that closed systems are systems that cannot exchange matter or energy with their surroundings. Open systems are systems that can exchange matter and energy with their surroundings. Earth is essentially a closed system when it comes to matter, but we are an open system when it comes to energy. So the amount of matter that we have on Earth, that's it. That's what we've got. That's our allotment. However, the energy, we are being continually supplied with it from space, specifically from our sun, providing us sunlight, which feeds plants and then helps run all these systems. We also are venting a little bit of this energy off into space as heat. The problem that we're worried about now is upsetting that energy balance and affecting the engine that keeps us all alive. All right, guys. That's where I'm going to end this. That's where I'm going to stop for here. I'll have a few more things to review with you, and then we're going to be finishing up Unit 1. So we are coming up to the end. We're going to have a Unit 1 test, and we're going to be done. We are going to finish this section out, and then we'll be moving on to Unit 2. So this is the end of the Earth Systems and Introduction to Environmental Science. All right, guys, that's all for today. I want you guys to take care. You have a great day, and I'll talk to you soon. Bye, guys.